In this video, we will explore an example of a stress concentrator. A stress concentrator is any feature on a body which decreases the maximum stress that body can withstand. We wanted to explore stress concentrators, specifically holes in rods, to see how they are affected under a tensile force. We also wanted to see if our results followed the same trend as the graph shown. The equation on the left is how we calculate the stress concentrator coefficient. We divide the yield stress of the material by the maximum stress in the subject with the hole in order to calculate K. In order to calculate the yield stress of the aluminum, we broke a control specimen in the Instron machine, and then divided the maximum pressure by the area of the beam seen in the top equation. Then, to calculate the different K values, we used the varying maximum pressures of the rods with the different size holes.
For our test setup, we used aluminum 6061 beams. After getting the proper material, we drilled varying hole sizes into those beams. This allowed us to see the results of different size stress concentrators in our beams. We also used a beam with no hole in order to see how close the known yield stress value of aluminum 6061 matched with our test results for that default beam. In order to do a proof of concept, we constructed these beams in SOLIDWORKS and ran FEA tests on them. The only normal stress in these scenarios comes from tensile stress, meaning the only applicable equation is sigma, being the normal stress, equals the applied load divided by the cross-sectional area. In each picture, the factor of safety is 1, meaning the beam will break. In our next slide, we will talk about what actually makes these holes a stress concentrator using our FEA analysis. In this figure, we see a beam that has undergone FEA analysis. It has been set up so that SOLIDWORKS indicates where the factor of safety is 1. That is indicated in blue, which is shown near the top and bottom of the circle. This shows us where the stress concentrator creates an acute rise in the normal stress experienced in the beam. This geometry creates an acute rise in stress because it creates a discontinuity in the beam, lowering the cross-sectional area that the load acts over. This is concurrent with the mathematical equation sigma equals applied load divided by cross-sectional area. As the cross-sectional area goes down, the normal stress must go up. Next, we will show you the videos of our real-world tests. No way. Are you serious?
And we had done the same setup 34 times. The one time that I made him watch it, the plate started to shift and turn under 50,000 pounds. It was ridiculous. Huh. And then you could see where it made like a divot.
As you can see, our calculated K values do not match exactly with the graph in the book. However, the K values do decrease as the radius increases. This may be due to the rate at which we pulled apart our specimens. We came to understand when using an Instron device, this variable can change the results radically.